My dudes, welcome to Handmade Data Structures in C. Today we're gonna be reviewing the most epic data structure of them all. It's called vectors. It's not Despicable Me vectors, unfortunately, or mathematical vectors. It's the programming vector, a type of list. I think Java calls them array lists, Python calls them lists, but it doesn't matter, they're all the same thing. They're just arrays that can be resized automatically. And the thing is, these are probably some of the most handy dandy tools on this side of the interweb, because first of all, you don't have to worry about you running out of space. Before I start, I probably want to distinguish a vector from another kind of list, because there are other kinds of lists. The main one you gotta worry about is a linked list, which is basically where you take a giant chunk of memory, or like at one point, and you just link it to another point. And you take those little chunk, and then each chunk has a link to the next chunk of memory, and it works that way. But who needs that right now anyway? Right now we're just gonna do vectors, because vectors are super simple, and so you might as well make one. But how? Why, you ask? The answer to how is C, and the answer to why is because we can. And let's get started. Alright, vector.c. Let's take a look. Well, actually, we're doing this from scratch, so I might as well just rm minus rf vector.c. Now we're doing it from scratch. So we're here with our vectors. So what's the first thing we need? So, well, a vector, like an array, has to have a method to get and set. So, since we're in C, we can use pointers. And pointers are basically, they deliver a location to your memory. It's pretty straightforward, okay? So, assuming I've got 100 bytes on my phone, right? And I have a vector, a pointer to byte 50. Then that's just a point. The value of the pointer is 50. But the value of what it's pointing to could be 1, 2, 3, 4, like a billion or whatever, and the pointer points to the bit in memory. Alright, so that's pretty straightforward. So when we give pointers, we are letting the user like change it or read it, and so that simplifies our get and set methods to just one, just get the pointer. So we need to have a get. What's the next thing we need? We have to make the vector in the first place, so like initializing the vector. And speaking of initialize, we also have something to deinitialize it, or like free all of the memory that's in use. And the fourth part probably is expanding the vector. You need to have some way to expand the vector. So like an insert method. Insert methods are pretty helpful, or something like that. And you need the inverse as well. You need to be able to shrink the vector, or at least remove elements from the vector. So the first thing that we need is the vector struct. So I'm assuming you have some basic familiarity with C. Yeah, I'm assuming you kind of know how to read, and if you aren't familiar with it, I highly recommend you familiarize yourself. Anyway, so the first thing that we're gonna do is so what are the things we need inside a vector? Now, like I said, a vector is just an array that can be resized. So obviously we need the array bit. Except there's a small issue with that. What type should we make the array? What kind of data should we be able to store in here? The answer is any kind of data. Any kind of data should be storable in here. If you think about it, what if you had to have a separate vector type for every single data type? It would be ridiculous. It would be insane. And I guess we're just gonna make it a void pointer, because a void pointer points to memory that can be any type. It doesn't really matter. It could be pointing to ints, it could be pointing to longs, it could be pointing to structs. It doesn't matter. It's all the same, because C is just not making any assumptions. So that's what we're going to use, a void pointer. And then when we retrieve the data, that's when we have to decide what kind of data it is. So we're kind of placing that responsibility on the caller to know what kind of data that they want from it. So we're going to use a void pointer. The next step is the capacity. The capacity is different from the actual length of the vector. There's a logical length to it, which is like logically how much. So for example, if I could have a vector which is 3 long, meaning it has indexes 0, 1, and 2, right? so that means its length is 3. But it could have a capacity to hold more. The capacity is how much memory is allocated for a vector. And that means how much space the operating system says the vector has. Now, it could have more, but the vector is currently 3 long, and that's how much it has. And the length and the capacity usually and should be different, but the capacity always has to be bigger than the length. If the length is bigger than the capacity, then you got problems. Probably a seg fault problem. Now, a seg fault decides the C program has violated a law of the land and decides to terminate it. Yeah, and so that's why we got up 2. And most people would just use it in for like length and an int for capacity. But this is not necessarily a good idea because an int can be negative. So we could either use an unsigned int or we could be intellectuals and use something called a size t. A size, because ints are undetermined of size. Like the C implementation gets to decide what kind of size an int is. And also you don't know how far you can index a vector. You see, on 32-bit systems, the maximum amount of memory you can get is 2 gigabytes, and that's like all indexable by one 32-bit pointer. However, on a 64-bit system, pointers are 64 bits, and so you can technically address like, I don't know, a lot of memory. I forget the exact number, but it's either a terabyte or a petabyte. And that's a lot of damage. So, if you don't want to get confused with this kind of stuff, you're best off just including making these a size t. A size t is always going to be unsigned, so you can't have negatives either. Like if you had a negative capacity, wowzers, that'd be wacko. Doesn't even make any sense. But with the size t, you're promising it's not going to be negative. And furthermore, you're also saying that it's whatever size an array is, which is good because that's what we want. Because you should be able to index an array with this length or index the array with capacity. So that's good. And as a matter of fact, there's one last bit that we need. It's called a load factor. A load factor just explains how much it expands each time. Because like when you resize an array, there's a part where you basically say, hey, I've hit my limits because the length is now equal to or greater than capacity and it's time to resize. So when you resize the array, you can either resize it just till the length, or you can resize it a little bit more and give yourself a little bit of buffer room before you need to reallocate again. And this is good because the more time that you give it to, the less you have to reallocate, because reallocating is kind of expensive, and we don't want that to happen so often. So let's make reallocation as rare as possible without using too much memory. And that's what something called a load factor is for. So we're making that a float. And basically what it tells is what percent to resize the array by each time. And that's just our vector struct. It's really simple. We just got the data, the length, which is the logical size of the array, the capacity, which is how much it can actually hold, and the load factor, which describes how much the capacity expands each time. Now, there's some headers we need to include for this. Because size t is actually not by default included. It's inside standard def. Include curses. And standard def includes standard lib. So we might as well include standard lib. Alright. That's the standard lib. And alright, we might as well include standard IO though, too. Because we're gonna need to print stuff inside the future. So let's talk about getting first. The first part about getting is what should it return? We're gonna return, for the purpose of this thing at least, a void pointer. Some people will say it's a better idea to have the function look kind of like this, right? It's not returning anything, and you give a pointer to the data you want copied over, and then the function will copy it. So like get like a vector pointer, and the data, and like you have a pointer, and then the pointer would be something like of course you'd have a size t describing how much you want to copy. right? But I'm personally a big fan. I'm not really a big fan, but I just think it's a whole lot more convenient just to return the void pointer instead of having it get past you. I mean, the reason some people like this is because you're getting kind of a guarantee that the data gets copied and there's no mistakes. With this, when you return the void pointer, at some point in time, like if you keep the void pointer in one place, and then you free the vector and you try to get that void pointer, you could be getting like a stale pointer because it's been dropped. So it's kind of like dangling and throwing to memory that you don't own, and that's a problem. But it's just so much more convenient that I'm like, you know what? It's better this way. Hence, I'm just gonna return the pointer straight up, no copying. I mean, there are some benefits, but I'm gonna guarantee though that the pointer that we return is valid until the next operation done on the vector. So this isn't the best for multi-threading, but if you're running a single thread application and you use the pointer immediately, it's not gonna be a problem. And the reason we do this is just so we can have like real cool stuff, like, you know, just like get, and you have, of course, you have your parameters, and you're just dereferencing that and setting it immediately to like 6, right? So much easier than having to have different get and set methods, like if we return the pointer, and because then we'd have to have like a set and a separate get. This one just simplifies things immensely, and it's not that bad either, in my opinion anyway. And we just have size t index. So wow, that function pointer is a whole lot easier. Let's just delete the old one. Yeah, so that's all we need. Of course, and to implement that, it's really simple. So this is where we do something called pointer arithmetic. You see, like I mentioned earlier, pointers just point to a location memory, but their actual values are something like 50. But the location they point to can be like 1,000, right? So if we add 5 to it, if we add 5 to the pointer, we won't get 1,005, because that's what it's pointing to. No, what we'll get is 55. So it'll be pointing to the 55th location memory instead of the 50th, and that's much different. So when we say v.data plus index, what we mean is that that we're not pointing to data, and we're not pointing to whatever memory is there at data. Now we're pointing to the memory location that is index bytes past data. And if we want to make it perfectly clear that we're talking about bytes and not whatever else a void pointer is, we should, just to be clear, make it bytes. So unit 8 v.data plus index. Boom. So what that does is it gives us the location of the thing, like the indexed location. So if, say, let's visualize this for a second. Imagine an array of bytes, and we want to get the second byte. So we just say vector 2, and that'll give us the second byte in the array, which is indexed, which is of course like the third one in the list, because there's byte 0, byte 1, and byte 2, you know? It's like that. And we're not actually returning the value of what's over there, we're returning the pointer of the thing, so that they can either get or set the data by themselves. See, that basically simplified it at least half, twice as much as having a separate get and set. So that was actually really easy. Of course, if we want to be really, really careful, we might want to add an extra check to say, if the index is greater than, then that's kind of an error right there. We want to say, whoops, that's an error. Actually, we probably want to make it a little bit more descriptive. Whoops. Index out of bounds. And of course we gotta add that new line. And then we'll exit. So now, next step, initialize function. So this one's actually really simple as well. We've taken a pointer to the, actually init is already a function inside the C library, so we should use something like a vector init. While we're at it, we might as well change this to vector get, so we're not conflicting with anything. Yes, it should be init vector. Beautiful. So, pretty much the idea is we just and we want to have an initial size, so let's define that. So the initial size is a constant that describes how large the array, the vector is when it's initially created. It is only about capacity. The initial length is obviously going to be 0. So the thing is, malloc 0 doesn't work, so we need to be at least 1. We're going to have 1 for the purposes of this, but most implementations will make it 10 or 16 or something that they find it works the best. But it's 1 for now. And we say v.capacity is equal to initial size. That was easy. v.length is going to be 0 because we don't actually have any stuff inside the array yet. We're going to have to expand it before we can do that. And there's one last bit. Load factor. Load factor, like I said, it describes how much it'll grow each time. So for this one, we're going to say 1.5. So what that means is, each time it hits the limit, it's going to grow 1 to 1.5 times the size. Like 150, 350, you know, the good stuff. And then free is even easier. It just, because all the other stuff is just on the stack, you know, like it's not allocated. Because when we malloc, we're basically asking the operating system for memory that might not get freed. But the rest of it, it will automatically free for us. So we gotta tell the operating system to make sure to free it. We just say free v.data. Real simple. Let's put a comment on top. And now we have the tough stuff. Expand vector and remove vector. So for expand vector, I'm gonna change this to insert actually. Because what we're gonna do is we're gonna make a function that inserts a specific amount of space into the vector. So it's gonna insert a solid. So let's say we're on byte number 2. Let's say we've got an array of five things, right? 5 elements. So we've got 1, 2, 3, and 4, and 0 of course. And then we want to insert 2 bytes at location 3. So now when I say 3, that's actually like the index number 3. So that's like just after the 4th byte. No, not the 4th byte. Well, whatever. I'm not good at counting, but you get the idea. We insert it after that, and this causes to expand to 7 bytes long if we insert 2 bytes. And yeah, the array has been expanded. If we insert at the beginning, then we get a little bit of room and we have to move everything over. If we insert at the end, then we don't have to move everything over, and we just like basically move it, basically extend the length of it. So that's why you get this, because it's a really flexible base function that you can do a lot with. So that's what we're gonna do. So first of all, let's try to think about what exactly we're dealing with over here. So I guess the first step is we're gonna make sure it's even a valid operation, because if the vector is too small, then we gotta do something about that. Like if it won't fit all of the stuff that we're trying to insert without increasing the capacity. So let's check that. If vector.length plus the actual, oh yeah, let me explain. there's some more operands, not operands, arguments we need to accept here. We gotta say, hey, what index are we inserting at? Or what location are we inserting at? And how many bytes are we inserting, right? So this one I'm gonna call it len because it's like the length, but it's different. So this is length. This is a length that we're inserting. This is a location that we're inserting them. Alright? Well, actually, I should just make this index to fit better. Index, yeah, sorry. So this is the index where we're inserting it. And if that's, but anyway, if the vector.length plus the length of however much we're trying to insert is going to be greater or equal to than our capacity, then that's going to be a problem, right? Because vector.capacity. Sorry, not vector. I'm foolish. It's v. It's spelled v. It's greater or equal then we have to remember to do resize vector. And next step is oh, speaking of which, I almost forgot. We have let me double check that. Okay, so resize vector. Curses. Yeah, after we make sure the vector is the right size for it, then we gotta start thinking about it. So the first thing we do, we increase the length of the vector because the vector is going to be a lot longer, isn't it? So vector the length plus equals the length of how much ever we're expanding it. So now that the vector logical length is longer, there's something we have to do. We have to move that memory back, so to speak. So now we've increased the capacity of the vector. We've increased the logical length of the vector. Now we have to move the data between where we're inserting, like the data between the location where we were inserting it, back length of bytes so it doesn't get overwritten. And the next step is, so to do that we're going to use the memmove function. So there are a variety of functions in C. Like there's memmove and memcopy. Both of these do the exact same task. They basically copy over memory. It's not that hard. To be continued.